Well, last time we were talking about converting to binary. I think it was the last thing we were doing, right? We were playing around with Excel and doing that. So one of the reasons why we want to play around with binary is because we want to talk about the way the machine represents numbers. So we started off by mentioning scientific notation and talked about that if you've got something times 10 to some power, whatever that happens to be, we know that. Why are you doing that? We know that this part, this Q, is always between 1 and 10. It's not ever equal to 10 because if we have it equal to 10 or bigger than 10, then we could just move the decimal point one spot again and change the power on the 10, right? So when we go to talking about how we're going to store numbers in the computer, rather than doing it base 10, we're going to store it in base 2. Because again, like I've mentioned, all a computer knows how to do is switch things on and off, right? On and off is nicely represented in binary. I promise I will give you a printout for the homework too. It's nicely represented in binary. So we're going to convert everything over to binary and talk about how to represent these numbers. To help us represent these numbers, we're going to switch over to a scientific notation in binary rather than in decimal, in base 10. So instead of having powers of 10 here on the end, we'll have powers of 2, because every time you do a power of 2, either way, that's what's going to move that binary point, right? That radix point, decimal point, right? Okay. So when we change to binary, we would have, I'll call it Q again, times 2 to the P. Now again, remember the reason why our Q here was between 1 and 10 is because if we got bigger than 10, we would just move the decimal point again. But now we're doing it base 2. So rather than powers of 10, each placeholder, each digit represents a power of 2, not 10. So if I hit a power of 2, that's going to move the binary point over a spot, right? Okay. So this number Q here is always going to be bigger than or equal to 1, like it is in scientific notation here, but it always has to be less than or equal to 2 or 1, 0 if you want to write it in binary. Because again, if it hits 2, then you're going to move the binary point again, right? So in particular, your Q looks like 1 point something with zeros and ones in it. If I could spell the word 0, that would be helpful. So the very, very first thing, no matter how you rewrite the number in binary, that very, very first non-zero thing that we're going to use for our Q will be a 1, no matter what. Well, if we do this in this scientific notation for binary, there's no reason to store this because you know it absolutely has to be a 1, without a doubt. Okay? So we don't bother storing it because it has to be a 1, all right? So the part that we'll actually store in the computer are 2 things. We'll store, well, there's actually 3 things, I lied. We'll store this part after the binary point. That needs to be stored, okay? We need to store the exponent, because that tells us where to move the binary point to, right? And then the last thing we have to store is it positive or is it negative? For is it positive or is it negative, we can do that with 1 bit. We call each of the binary digits a bit. Bit is short for binary digit. Okay. We just need 1 bit for the whether it's positive or negative. Then we'll have a series of bits that'll help us store the exponent, and a series of bits that'll help us store this decimal part. This decimal part at the end we refer to as pardon me, the mantissa. I believe it may be called 1 plus mantissa or 1 point mantissa. It doesn't matter. So we got the mantissa part that we will store. That's the decimal part. That's what they call it. It's actually called, the whole thing is called the mantissa. So this is 1 plus mantissa part that we're using as far as the form goes. I don't really care about the words, just telling you what it is. Okay. So one of the first examples they do in the book is talk about how you can store these things in smaller computers, and then we talk about actually how the computer stores things in different precisions. So, pardon me. Let's say we have 1 bit for the sign, 3 bits for the exponent, and let's say 3 bits for the mantissa. How many different numbers can we represent? This is a starting point. They do a little bit. They go through an example, and then also talk about sometimes 2 different representations are giving you the same number. This doesn't happen in what we're going to end up doing, but so let's think about choices that we could possibly make. So they use kind of boxes to denote the bits. I'm just going to do underline so I don't have to try to draw boxes each time. So here would be your sign bit here. The first ones are going to store your exponent. And this part will be the mantissa part. And we can just start talking about how many different choices we have and then how many different things can we store. Well, each of these, pardon me, each of these are going to have 2 options, right? Because I got a 0 or 1 I could put here, 0 or 1 we can put each of those. So if we're looking at just different representations that we can store in here, how many choices would we have? 2 to the 7th, right? So if we just fill out these bits, we would have 2 to the 7th different choices, right? Now, one of them, hopefully, is pretty straightforward. There's 2 of them that should be representing the same number, even though they might look different. And we're going to talk about playing around with how we're going to deal with the exponent to make sure we get some small numbers and some big numbers. But if I say I used all zeros here to give me the number 0, then plus 0 and minus 0 would be the same thing, right? So that would be 2 that would be the same thing. So using all zeros gives you a special case that you end up with 2 of the same thing. Another special case that pops up is if your exponent gets really, really big. If you use all 1s for your exponent, that's telling you that you're getting something really, really huge and letting something be going off to infinity. So all zeros is a special case to represent the number 0. All 1s for your exponent is also a special case because that's going to represent going off to infinity or minus infinity. Positive infinity if this is a plus, minus infinity if that's a minus. Right. So that usually the convention is if it's 0, it's positive. If it's a 1, it's negative. But if you use all 1s for your exponent, that's saying that you're using 2 to the biggest possible power that you can. That's the power that's on the 2. So using all 1s throws it off to positive infinity. And then if you have the sign bit being negative, it'll throw off to negative infinity. So there's a couple of choices that get thrown off to start with. So really, we got 126 different numbers that we could possibly do here because we got. Sorry, that's not true. Yeah, that's 126. So I'm not going to use positive or negative infinity, but I could still use 0. But two of those choices are the same number because you get positive 0 and negative 0, right? So two of the choices go away because two of them are representing positive or negative infinity. And then, of course, that's assuming if you've got the number, oops, hey, 1, 1, let's say we did something like this. I'm saying that's representing positive infinity because this exponent is too big. But of course, if I change any of these bits, it's also going to be even bigger, right? Because again, this would represent 1 times 2 to the 4 plus 2 plus 1 would be 7th, the way I've got it written right now. Because this would be 1.000 on that. Because remember, there's an understood 1 right here. Unless everything's all zeros. There's an understood 1 right there. Right? If you change any of these digits here, then this is going to make it even bigger. So we've got several numbers that are representing positive infinity or negative infinity. Because anytime this exponent gets big enough, the computer is going to kick it to infinity, is the idea. So it doesn't matter what these are. Does that make sense? So in that case, we get what's referred to as an overflow. It's just a bigger number than the computer is going to handle. You get an overflow positive infinity. You also get an overflow negative infinity. You probably had those errors pop up on your calculator or the computer before. The number just gets too big, and it's just like, nope, I'm done. I can't represent that number anymore. As far as representing it as a specific type of variable, there are ways to handle letting your numbers get really, really, really big. You just have to use other spots in memory to play around with different things. So that's why you've got different computer programs that can take really large, say, factorials. If you start putting things in your calculator factorial, I think 69 factorial typically is the biggest one you can get when you get to 70. At least that's what scientific calculators used to do. Might go a little bit bigger now. But there are things that you can calculate really, really large factorials because it'll just start storing to the different pieces in memory rather than trying to store it as a single variable entity in the computer. So there are ways around it. I think Dr. Ross said that Python is called long int, maybe? Something like that. Whatever, it doesn't matter. The point is that what we're talking about is using a single location in memory for a variable, and this is how it's going to get stored. There are ways to work around that you have to use other memory areas to do that, which is beyond the scope of what we're doing. All right, so anyway, even though it looks like there's 2 to the 7th choices here, pardon me, we really have other choices that aren't going to work. So anything that corresponds to 1, 1, 1 here is not going to work as a number, okay? Because it's going to overflow the computer, whether it's positive or negative. So for this 1, 1, 1, we've got another, 16 ways? Right? So for that specific one, there's 2 choices for that, 2 choices for that, 2 choices for that, 2 choices for that. So that throws out another 16 possibilities for numbers. Right? Because this could be 0 or 1 for each of those. Okay, so we've lost one extra choice because two of the representations for 0 are the same thing. And then we've got 16 other ones that go away. Right? So even though totally we would have 2 to the 7th choices because we'd have 2 for each bit, two of them represent the same thing. They both represent 0. And then we've got 16 of them that all overflow to infinity, either positive or negative infinity. So really, at the end of the day, we lose some numbers. We end up with what? 128 minus 17, right? Because you get the 16 that are all overflowing to infinity and the 1 for 0. So it looks like we got 111 different things that we can represent. Does that make sense? Again, the idea here is just, we're talking about representing these things. Part of it has to be the exponent, part of it has to be the antecedent. This is just an example. There's obviously, when we're going to talk about longer numbers being stored, so these numbers, this total number of different things will be even bigger. But the main thing I want you to get out of this is that once you hit too big, everything's going to be too big. Okay? The other part is that we also get a problem when things are getting too small, right? And then there's one other problem that I want to mention. Eventually, there's only a smallest thing that you could possibly get here that's non-zero, right? The way I've got this written right now, I could use an exponent of 0, right? But if I use an exponent of 0, I can't use all zeros here because that's going to be a special case. It's going to represent 0. The smallest thing I could represent here would be a 1. So the smallest thing here that you could represent is 1.001 times 2 to the 0, the way we have it written. Because again, I can't use all zeros because that's going to be a special case for 0. So the smallest thing, the way we've got this written, the smallest thing we could represent is 1.001 times 2 to the 0. Each of these is a power of 2. So this number would be, 2 1/8? Because that's a half, that's a fourth, that's an eighth in binary. Each was the a power of 2. 2 to the -1, 2 to the -2, 2 to the -3. That would be right. The way I have it written, that's the smallest thing we could possibly do. Right? Again, remember, there's an understood 1 here all the time. No matter what, there's an understood 1 there. So the way we have this written, the smallest thing we can represent is something just a tad bit bigger than 1. That seems not very useful. I don't think it's very useful, right? In particular, I don't have any fractions that we can represent that are smaller than 1. That's the way we have it written. So the way you work around that when you represent numbers is that you kind of split your exponent in half. That's the idea. So if I use these 3 digits for exponents, well, your numbers will go from 0, 0, 0 all the way to 1, 1, 1, right? That would be your possibilities. So in particular, in decimal, this exponent is 0. In decimal, this exponent is 7, isn't it? Okay, so remember, each of these places is a power of 2. So this is 2 to the second. This is 2 to the first. This is 2 to the 0. 4 plus 2 plus 1 is 7. Okay. Sorry. I'm glad you asked. Yes. Mm-hmm. So again, each place is a power of 2. So this is 2. This should be a 1. My bad. This should be not 7. I lied. This should be 9 over 8. I was thinking of that being a 2. That's 2 to the 0 power. It should be a 1. My apologies. This is 1. This is 2 to the 0. This is the 2 to the -1 spot. This is 2 to the -2 spot. 2 to the -3. I was thinking of that as 1 times 2 rather than 1 times 1. Sorry about that. So it should be 1 plus an eighth. So that's 9/8. I wrote 17/8. I was thinking about it as 2 rather than 1. That's where the eighths comes from. Still, it illustrates the point that I can't get less than 1 the way we have it. Are we all on the same page for how I'm getting these numbers now? Yeah, Lainey.
Why is the farthest right 2 to the 0? Why isn't it 2 to the first? Because isn't the 1 that's always there the 2 to the 0?
I'm looking at the exponent right now. I'm just looking at representing the thing that's going to be in my exponent. So anytime that understood 1 corresponds to the mantis part. I'm talking about representing this piece right here. This is the part that's going to move this decimal place either this way or this way, depending on if it's positive or negative. So that's not going to have the understood 1 on it. It's the mantissa part that'll have the understood 1 on it. Okay. Are we okay at how I got 7 out of this? Okay. All right. So basically, we're just using what's called the expanded form of a number. Rather than doing powers of 10, we're doing powers of 2 since it's in binary. Okay. Anyway, these are my possible exponents, but I would like to be able to get some decimals, right? So what we could do, well, and this is exactly how we handle it. The idea here is kind of try to split this in half as much as we can. It's not going to be exactly in half. But it'd be nice to have some negatives and some positives. The negatives representing moving your decimal place to the left, and your positive representing moving, your binary place to the left, right? Your binary point to the left, some representing moving your binary point to the right, right? So if we were doing, let's say we had an example of scientific notation. If you've got 3.17 times 10 squared, what's that the same thing as? 3717, right? But if you've got 4.82 times 10 to the negative 3, what do you get? Yeah, exactly. So that's telling you to move left or right, right? We'd like to be able to do the same thing here. Okay? So what we do, since we only have this spot where we can represent the exponent, we essentially try to split it in half. Now, of course, one of them we'll use as 0. So it's not really half because you'll have one fewer positive than negative or vice versa, depending on where you put the 0. Okay? So right now what we could do, say we could go from, usually we do one fewer negative than we do positive, just as a standard. So what we could do here is instead, at 4 would be in the middle essentially, make that 0. Then what would 7 be? If I say 4, I'm going to, when I take a 4 out, that's giving me really a 0 exponent instead. What would your 7 represent? If we're moving the 4 down to 0, the 7 is going to represent 3, right? We're just shifting everything down 4. And so then the way I have it written, this one would be negative 4. This is actually backwards of what we typically do because now I've got more negatives than positive. I got one more negative than positive. But that's the idea. If I pick somewhere in the middle to be 0, my 0 exponent, then I get some that are negative and some that are positive. Right? Okay. All right. So this is how we're going to handle when we do these things in machine representation for these different numbers. We're going to shift our exponent so that we get things right in the middle. To split, we get some positives and some negatives so that we get decimals, right? We get things that are smaller than 1. Right now, the way we had written things, we don't have anything smaller than 1, but we would like to be able to represent things smaller than 1 and bigger than 1, right? So the idea here is to use that exponent representation that gives me something between 0 and how many ever bits that we have, and move it so I split it right in half so we get some negatives and some positives. That's the idea. Okay. So in this case, the way I have it split, now the smallest thing that we could possibly represent, if I use 0, 0, 0 for my exponent, that really is representing a negative 4 exponent, right? The way we have it. Again, I can't use all zeros, so I have to have at least a 1 here. So then the smallest number in this case would be 1.001 times 2 to the negative 4th, the way just from what we wrote, right? Again, we can't use all zeros. That's a special case of for 0. Something has to represent 0, right? So the reason why it's a special case is because, again, we say there's an understood 1 there, but there can't always be an understood 1 there for every single case because we have to represent 0 somehow. So this would be the smallest possible thing that we could represent. This moves your binary point 4 places to the left, just like it would in decimal. This is base 2, though, right? This is 1/2, 1/4, 1/8, 1/16. 1/32, 1/64, 1/28. Right? Remember, these are negative exponents, right? 2 to the -1, 2 to the -2, 2 to the -3, 2 to the -4 is 1/16. Yeah. It's just like decimal, except for we're doing 10 to the -1, 10 to the -2, and so on. We're doing 2 to the -1, 2 to the -2. Okay. So we get a 16th plus a 28th. 16 times 8 is 128. Yeah. So we get 9 over 128. Let me simplify that. That's the smallest in absolute value, the smallest positive number we can represent in this system. Okay. There's always going to be a largest possible and a smallest possible number that you can represent in machine representation. Okay. So anything that's smaller than this, your calculator, your computer will just treat like it's 0. Okay. Rather than overflowing off to infinity and stopping, like it does for really, really big numbers, your calculator or computer, when it hits that value, will just automatically underflow to 0 and treat the number as 0. So we actually call it an underflow rather than an overflow. And it'll just treat it as 0 when it's done. Okay? And you see that on your calculator or your computer or what have you. If you start looping through things and say you divide out by 2 every single time, and eventually it'll just quit, right? You get 0 every single time. You can see that on your calculator pretty quickly. Let me open that up real quick and just show you what I mean. Maybe. Maybe. I can hit the right buttons here. I would have thought about using this earlier, I would have had this open already. All right, so let's say I put in just 1 to start with, and then take the previous answer and divide it by 2. I know it's going to take a little bit, but eventually, I keep dividing it by 2. Eventually, someday, okay, if I would have done this before class, I would have realized it took this long. Okay, let me start over. Let's not divide by 2 every time. Let's say we divide by 100 each time. I just wanted to illustrate that eventually it's going to treat this thing as... Yeah, this one should be... Is it going to get to 99 and it'll stop? Yeah, eventually it just hits 0. That was the whole point. Okay. It depends on what your machine decides is 0. If you do this in R, it'll actually kill it at about 2. I could have wrote a small R program to do this more quickly. It'll kill it around 10 to the -16th. Anything less than that will be about 0. That'll treat it as 0. The entire point of this exercise, rather than me clicking on it 1,000 times, okay, was just to show you that eventually you can't represent every single number. Eventually the machine says this is 0 and I'm done. Okay? But it also treats it as 0 rather than gives you an error, because it doesn't want to necessarily kill it because it's dealing with something really, really tiny. Okay? So it just underflows it to 0. The only issue you would have, of course, if it automatically underflows it to 0 is if you're saying dividing by that particular number. And in that case, it wouldn't give you the error, just trying to divide by 0. All right. In any event, no matter what number you try to represent on a computer, there's eventually a smallest thing that you can represent, period, in absolute value. So every single representation, no matter what you have, is always going to have what's referred to as a hole at 0. There's always going to be some tiny little interval around 0 that you just can't possibly represent those numbers. So there's always something really, really tiny. Now, hopefully, whatever applications you're doing, that won't matter, but just know that it's impossible from a computing standpoint to represent every single number. So there's going to be tiny, tiny numbers that you can't represent. There's also going to be a whole slew of numbers that you can't represent exactly. You know from experience that when you look at fractions, either their decimals terminate or they repeat. Or if you have irrational numbers, those never terminate and never repeat. But regardless, if you're representing a number on a computer, no matter how much space that computer has, there's not infinite representations of anything, right? Eventually, the representation has to stop. So there's going to be a whole slew of numbers that you cannot represent exactly. Most everything, every number that gets put into a machine is approximated. Even a tenth, if you try to do 1/10, that's going to, in binary, that's not going to stop. Okay? Because you got to figure out a half into, or it's not a half, it would be what? A 16th is the first thing that goes into it. And then you go try a 32nd, try a 64th, try a 128th, right? Remember each time we multiply by 2 and peeled off the exponent part? But think about what has to happen. Oops. You're taking this 1/10, we would multiply it by 2, and then whatever piece is left over, you'd multiply by another 2, multiply by another 2, and so on up the line. Are you ever going to cancel out that denominator? No. So that representation as a binary decimal implies base 10 again, but as a binary decimal, that's not going to stop. In decimal, we know that any fraction that isn't all 2's and 5's in the denominator will repeat. So like 1/3 is 0.3 repeating. The reason why is you can never cancel out a 3 in the denominator by keep multiplying by 10. Right? But if it's made up of all 2's and 5's, you can cancel out the denominator, right? By eventually with a power of 10, but that's it. So if you have any other factor that's not a factor, a power with 2's and 5's in it, it's going to repeat as a decimal. Same thing's true in binary. The only thing that will terminate are powers of 2 in the denominator. Everything else is going to repeat eventually. Or I shouldn't say powers of 2. I should say sums of powers of 2. Because I can take a high of power 2 to kill all those denominators. Yes.
So one more example, when you get the 1/16 plus the 128, is that just where the one falls?
Yeah, this is where the ones are falling. Yeah. So the ones are representing the non-zero placeholders there. The non-zero 2's to whatever power places. Yeah. All right. I think I've rambled on enough about that. So let's talk about how we actually represent these things with machines. So there's a couple of different precision levels that we'll have that we'll talk about. Oops. We'll start with single precision. All of these are referred to as floating point forms or floats. Single precision uses 32 bits to store a number. Here's the way the allocation works. Well, again, we want to keep track of whether or not the number is positive or it's negative, right? So 1 bit is for the sign. Whether it's positive or whether it's negative. Typically, we represent that as the first bit. We think about 32 bits long. We usually think about the sign bit as being the first one. Then we use 7 bits for the exponent. Nope, sorry, I lied. We use 8 bits for the exponent. That leaves us 23 for the mantissa part. Again, the 23 doesn't have the leading 1 that's stored in it, but this is the way we represent single precision numbers. Right? So let's talk about the types of numbers that we can represent and then play around with numbers that are being represented in that case. So again, we've got something that's in the form of plus or minus, because that's going to be our sign bit, q times some 2 to the p, right? This q part, and this is just the way they write it in the book, this q part we think of as 1 point some decimal part. They use an f to represent that because it's this f that you're actually going to store. Because again, we assume that the 1 is on there all the time. Does that make sense? Okay. So that f part, we're going to have 23 bits that we can store that f part in. Okay. That'll be in that last part. And again, the way the book visualizes it, if you think about things being stored, this one comes first, this comes second in the list, and this one comes third. Okay. We're going to practice with pulling these things apart and see what number is being represented. That's the only reason why I'm mentioning it. Okay. First bit's the sign bit, the next bit's the exponent, or the next 8 is the exponent, and the last 23 are the decimal part of that 1 point whatever. Okay. All right. Then we talked about splitting this thing in half, right? If we look at the exponent piece, this exponent is 8 bits, right? So if you've got 8 bits, 8, okay. Well, your possible numbers that you can do are what? Well, I could do all zeros, or I could use all ones, right? Agree with that? So the lowest, of course, if I'm using all zeros, that must be 0, right? Okay. This is, there's a faster way we can do this, but this is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, right? 2 to the 0 place, 2 to the first place, 2 to the second place, third, fourth, and so on up the line, right? Well, rather than adding all that together, this number, if you think about counting in binary, you'd have 0, 1. The next number is going to be 2, but 2 in binary is 1, 0. There's 1, 2, and no 0 and no 1s. 3 is 1, 1. What's 4? 1, 0, 0, right? That's 1, 4, or 1, 2 squared. No 2s, no 1s, right? So on up the line. Okay. Notice that here, this number is 2 to the first minus 1. This number right here is 2 to the second minus 1. I'm developing a pattern. There's 5. There's 6. There's 7. Right? This is 4 plus 1. 4 plus 2. 4 plus 2 plus 1 is 7. Right? What would the next one be? 1, 0, 0, 0. Right? It's like getting to 999. The next number is 1,000, right? I got to move it. I've run out of spots. Okay. Notice the one right before it is 2 cubed minus 1. Right? The reason why I'm saying that is I'm trying to figure out what this number is quickly. Notice here, I've got 1, 1. That's 2 to the first minus 1. I've got 2 1s. This is 2 squared minus 1. 1, 2, 3 1s. That's 2 cubed minus 1. How many 1s do I have here? 8. So what number is that representing? 2 to the, I got 8 1s. Is going to be 2 to the 8th minus 1. Yeah. So that's 255. So the numbers that can go in my exponent are I can go 0, that's as low as I can go. I can go to 255, that's as high as I can go. Now again, these are going to represent special cases. All zeros and all ones are always representing special cases. Basically, it's a special case of if I see all zeros, I'm going to underflow to 0. If I see all ones, I'm going to overflow to infinity. Okay? So we're never actually going to hit 0 for that exponent. We're never actually going to hit 255 for that exponent. So really, your exponent is going to end up being between 1 and 254. Okay. All right. That's just more technical than anything at all. It's just that those are special cases. Somehow we have to tell the machine anything smaller is just 0. And somehow we have to tell the machine anything bigger is way too big. So we're going to quit either way. Okay? All right. So smallest exponent. So this p-value that we have up here, your book actually uses an m, I believe, but that's doesn't matter. This p-value here is going to be between 1 and 254. That's your possible exponents. Now, to get a number that's represented again, like I mentioned before, this doesn't allow me very much playroom. If my exponent has to be positive, then I can't represent anything that's a decimal. Decimal, it is less than 1, right? Fraction, to use a better word instead of using decimals, it's applying to base 10. So just like we did before, the trick is that we're going to shift everything and know that we've shifted it. Okay? So that we get half of them roughly negative exponents and half of them positive exponents. So what we're going to do here is we're going to shift by half of this number. We've got 254 here. We'll subtract 127 and move everything, shift everything 127 to the left essentially. Okay? So if we do 127, this will be negative 126 is the lowest exponent we could use. Actually, I should have used P is probably not the right letter, but that's okay. And then this will be 127. Just write it as exponent here. So the numbers that we're going to represent are going to be, our lowest exponent that we can use is negative 126. So that would be the smallest number that we could possibly represent. And then 127 will be the highest exponent that we could represent. And that's the exponent on the 2, right? So what this tells us is that the smallest possible number that we can represent in single precision is what? Well, I just said that I could have 2 to the negative 126 is the smallest negative exponent we can use, right? And then the smallest possible thing that you could have for the mantissa that would correspond to that would be 1 point, a bunch of zeros. Because if I put anything that's in that bunch of zeros with a 1 in it, that makes it bigger, right? That's going to make the decimal a little bit bigger. So the smallest number that we can use is 1 times 2 to the negative 126. That's the smallest positive number or smallest in absolute value negative number that we could possibly represent, period. Okay? I'm talking about when I said smallest possible number, I really mean positive because the negatives are just the other side. Okay? I'm worried about the smallest magnitude of number. Does that make sense though? Yeah, Lenny.
In the last one, didn't you say that it had to be like, because there was 3 bits, it had to be like 0, 0, 1 was the smallest it could be?
Yes.
So then why can this one be all zeros?
It can't. That was why I moved the 0 to the 1.
Okay.
All zeros would have represented the small, so all zeros would represent an exponent of 0, right? So in this case, if I would have So we're going to handle that as a special case. So we're just going to eliminate that special case, move this exponent to 1, and then shift everything down 127 automatically. So whenever I have it, so the smallest exponent you can actually put in there is all zeros with a 1. So that would be, if we weren't worried about shifting, that would be 2 to the first in that case. Right? No? No? So if I look at my exponent up here, I'm saying anything with this we're going to throw out. Okay? So then the smallest thing I could actually do is change that to a 1. If we don't shift, that's 2 to the first. Would be the smallest thing we could represent. Okay. I can use it as long as this isn't all zeros, I can use all zeros on the mantissa part. I just can't use all zeros on the exponent part. So maybe that's where the difference is lying. So if this is all zeros, then I have a problem. Okay. So the smallest I could do is a 1 here, but I don't want, this doesn't allow me anything to be fractional, right? I don't want to get anything small. So that's when we do this shift, and now this is the smallest exponent we can do. And then to correspond with that, the smallest mantissa we can use is 1 point, a bunch of zeros. Because as soon as I put anything on the end, it'll make it bigger. So that's the smallest one. For largest, I can't use all, well, the largest possible exponent is, what would we say, 127, right? That was the largest possible exponent we could use, right? And then we can do 1 point, whatever that is, 1.111 dot 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 dot. So there's 23 ones here. That'd be the smallest, or the biggest that we could use. There's 23 bits for those ones plus another 1, right? We agree with that? Okay. So what would this number represent? Well, this is 2, without a doubt, right? But what are these here? This is a half plus a fourth plus a sixth plus all the way down to 2 to the negative 23rd, right? So we could actually add that up. If you remember some series stuff that we've done before, we do a half plus a fourth plus a sixth. We've got I'm not going to go through the derivation of the formula, but we've got a common ratio here of a half each time. So I could add this up. If you had an infinite series, it'd be 1 over 1 minus r. We've done geometric series in calculus, right? This is going to be 1 minus, it'd be a half to the 24th over 1 minus a half. Want to add all that stuff together? Oh, it's an eighth. I don't know why I wrote a sixth. Thank you. This will be a 2 on bottom, so this is 2 minus 2 to the negative 23rd when we're done. That's just this piece right here. And then you would add a 1 to that, or sorry. That's 1 plus that, I should say. And then multiply by the 2 to the 127th. Oh, I forgot. I'm sorry. This is that value. We'll say that again.
Is that 2 times 2 or 2.2?
That's 2 minus. Yeah. I'm sorry. I forgot to put the 1 in there. I already have the 1 in here for this. Sorry. This geometric series, this does start at 1. So this is 1 plus all of that. So this is equal to 2 minus 2 to the negative 23rd times. Oh, for heaven's sake. times 2 to the 127th. And if you simplify that, you should get something like 3.4 times 10 to the 38th, roughly. Sorry, I messed up my geometric series there. I forgot that 1 plus was in there. Again, in single precision, the only reason why I'm going through this is just telling you in single precision, what's your biggest number you can do, what's the smallest number you can do. I know, not the most interesting of days. So let's see if we can do a problem here and see what's going on. All right. So let's say we wanted to represent one of these numbers in single precision. Double precision, all it does is just give you larger exponents and longer mantises that you can use. Double precision does 64 bits rather than 32. Okay, so you end up with like I said, you end up with longer exponents and longer mantises that you can use. So, but we're just going to concentrate on the single ones because you're all very excited about it anyway. All right. So let's look at, this is number 4 in your book on page 52. This is actually part D. Let's look at the number 0.234375. We're going to do the machine representation of this. So for single precision. So again, first bit is the sign bit. Since this is positive, what's your first bit going to be? 0 or 1? 0. Yeah, so 1 will refer to negative. Okay. 0, your first bit will be 0 in this case. Okay. All right. So then you've got 8 bits to use for your exponent, and you've got 23 bits to use for your mantissa piece. So the first thing I need to do is convert this over to binary and see what we got going on for the binary representation of this decimal part. All right. So let me flip over to Excel real quick, which I didn't save it, but we should be able to recreate this pretty quickly. Hopefully you saved your worksheet. The number here again was 0.234375. Remember to convert this to binary with a decimal. What was the first thing we did? Yeah, we multiplied it by 2. When we multiply by 2, basically all we're doing is shifting the binary point over and seeing if there should be a 1 or a 0 there, right? Okay. Notice in this case, the first part is a 0, so that's the digit we actually want, right? So we picked that off using the int command. You could also use the floor command. It doesn't matter. So that'll be our first one in the left place, yes? Okay. All right. What did we do here? Yeah, it was B1 and then minus that, right? Because I need to pull off the integer part if there was an integer part. Okay. Then we copied that down 1 row. And then pull. Notice in this case, this terminated, right? So what that tells us is it terminates with binary. This tells us that this number must be a sum of fractions that have 2's in the denominator. In fact, it's an 8th plus a 16th plus a 32nd plus a 64th. I know it's those because remember again, this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 4, 5, 6. That's how I read those, right? Each place is representing a power of 2 now. And since we're doing decimals, number less than 1, it's negative exponents. Okay. All right. So if we write this in our scientific notation form for binary, I'm going to move the decimal place 1, 2, I'm sorry, not the decimal point, the binary point, 1, 2, 3 places down, right? So this will be 1.111 times 2 to the negative third. Okay? So this is 1.111 times 2 to the negative third. And I'm going to put a little subscripted 2 there just so that we know that we're in base 2 here. Yes.
Did we get the exponent when we reached the first one?
Yeah, the exponent is because the form of it needs to be 1 point something. So as soon as you get to the 1 point part and how many places you move, that tells you what that exponent is. Yep. Not unlike what it is for scientific notation in base 10. It's the same idea. We're just using base 2, so that's why it's 2 to the negative third versus a 10 to the negative third. What does the 2 subscript mean? It just means that the number is written in base 2. Yeah. I don't want to write it as 1.111 times because, and not without a base, because then it might that's ambiguous for what base I'm talking about. I mean, everything we're doing is in base 2, but it will only be ambiguous. I'd rather not be ambiguous. So far, so good? Okay. So here, again, if we think about 32 bits, the first bit will be 0. I'm going to leave a spot for the exponent. Leave a spot here because we're going to do 8 bits for the exponent here in a second. But what's the mantissa part going to be here? What do we need? Do we need to store this first one? No. So I just need to store 111 and then a bunch of zeros, right? So the last part will be 111 0 0 0. And how many zeros will be here? 20. Good. Yep. Because there's 23 spots to store all of that. I just don't feel like writing 20 zeros. Does that make sense? The part after the binary point gets 23 spots to put in, right? The end of them is just all zeros. So it's just those 3. Yeah.
Why is the first one 0?
This is because the first bit is your sign bit, and since it's positive, we use a 0. If it were a negative, you use a 1. Yeah. All right, let's worry about the exponent now. Remember, this exponent, when we represent this has to be a positive number. That's all we have, right? So to change this negative back to the positive, we need to add what? What did we subtract off to start with? 127, right? So we're going to store -3 plus 127, or 124. Right? Because this has to be something between 1 and 255. Or excuse me, 254. Those are your possibilities in binary. How that's written, right? That's how that's expressed. We understand that 1 to 254 really is -126 to 127. Okay. So the other part we need to do is convert this to binary. Okay. Jump back over to Excel. What do we do first? We're going the other way. This is the whole number part. We got to divide by 2, right? This one gets divided by 2. Right? And then we want the remainder. Yeah? So what did we type in here?
F1 minus in parentheses around 2 times G1.
Okay. So we did F1. And then minus. And then, well, the one we did before was general, right? So we could change the base, but here we're just interested in base 2. So 2 times G1, right? Because we're trying to pick off the remainder. Yeah. And then this is just copy this back down. That's what we're going to divide into next time. Highlight. And then highlight all of them. Again, if you saved your Excel file last time, you should already have this. Ooh. I didn't do that right. So I didn't do something right. Oh, I gotta be careful. I need to do. That's not quite right. I need to do the integer of that, don't I? Because I don't want the fractional part that's on there. There we go. No, it didn't work. What did I do wrong?
You get the integer on the G1.
Oh, yeah, you're right. Sorry. I want the integer on the whole thing.
In the G1 still.
Say that again.
When we divide by 2.
Oh, right. We did the integer here. That's right. Either way works. Yeah. Sorry about that. That's better. This is why you should save your things. I don't have to retype it each time. Okay. All right. When we get to 0 here, we know we're done. Right. Okay. So then we go, this is your 1's place, 2's place, 4's, 8's, 16's, 32's, 64. Yeah. So your 124, go back over here. This is 1, 1, 1, 1, 1, 1, 0, 0. 4, 8, 16, 32, 64. Oops, too many. Is that what I did? Did I do too many?
Shouldn't there be a 0 in the front?
Oh,
Because it's 8 things.
right. That's what my problem was. I just wrote too many ones. Thank you. I did 6 1s instead of 5. There were just 5 1s, weren't there? 1, 2, 3, 4, 5. Yeah, there were like only 5 1s. There should be a 0 in the front. Sorry about that. Okay, let me go back. Let me erase this 0 to start with. I just got a little excited. I wrote too many 1s. Okay. It was 5 1s and 2 0s, yes? Okay. That's only 7 binary digits. Yeah? But we need 8 bits here. So we'll fill the front with a 0 here. Why are you not writing? Yes.
Why are the 2 zeros at the end of the ones?
So remember, we work top down and go to the left. So the first remainder was a 0.
Oh, okay.
Yeah. So we're working top down.
So, yeah, we're going
Yeah. We're going. Yeah. So this is your 2 to the 0. This is 2 to the first, 2 to the second, and so on down the line. So you always go. If you want to think about writing it down, you always write it down this way. Okay, so notice that when I write this down, if I go from bottom to top, the number is 1, 1, 1, 1, 1, 0, 0. Right? There's only 7 spots taken up. We have 8 bits, so we're going to put a 0 on the front so it doesn't change the number. If I put a 0 on the end, it moves everything over a spot, and so it'll make the number different. So that's why the 0 goes on the front. Seems like we could do another example. Okay. This is part, I'm just going to write it on here so I don't have to keep going back and forth to my notes on Notepad. Or OneNote. 492.7812. What happens? 125. That's the number we're going to change. So we're gonna change the whole number part, and we'll change the decimal part separately. So there's 2 different processes, right? This one we keep doing repeated divisions by 2. This one we keep doing repeated multiplications by 2. Right? But we've already got our stuff set up. So we should just be able to change our spreadsheet here What should I change this number up here to? Up in the upper left-hand corner. It would help if I put a decimal point in there. Yeah. And then up here, I'll have to copy down, but up here instead of 124, we'll have the 492. So far, so good. Just that was why I had the spreadsheet set up, right? You can also write an R program to do this. Write a Python program to do this. You can write a insert programming language to your program to do this. Java, C, C++, C Sharp, Fortran, COBOL. Yes. Here. You just need to go. You need to make sure you go all the way down until that turns to 0. Oh, the first one? We multiply by. Okay, so whatever's here, you want to multiply that by 2. And then you want to pick off the integer part of that. So there's a whole piece of that. And then highlight just those two to start with. So it does not fault it. Highlight. There you go. Fold it in. Just go back to that one. There you go. Don't go back to it. Now fold it down just in one spot. Just one spot. And then highlight all 3 and pull them. No, highlight just the row. And then go all the way pull it down. Just that one. Stop at the 1. Stop at the 1. Okay. No. Let's do those 3. Just highlight them though. You don't want to turn black. Just highlight it. There you go. You want the big white plus to start with. The big white plus to start with. Let go. Let go. Let go. Go back over towards the white plus. See this white? Yeah. Now just click and highlight while it's white. Because you don't want to copy that over. Just click and highlight while it's white. Right there. Yeah, click and highlight. One more. There you go. Now go to that one or just don't turn black and pull it down. There you go. Now keep going. Yep, there you go. Now you got it. There it is. Yep. All right. So what does this number look like? All right. So now we should have both the decimal part and the whole number part converted. So what is this number base to? 111.001. Base 2, right? Because again, we write the whole number part that way, and write this part that way, right? What do we do next? Shift the decimal point over, and it's going this way in this case, right? How many places does it get moved? 1, 2, 3, 4, 5, 6, 7, 8. Yep. So this is 1.1110110011001 times 2 to the what power? Well, it's 8 to start with. Yeah, good. Okay. So we moved it from here to here. I got 8 places that we moved it, right? So that's why this exponent is an 8. Right? Yes.
How do we know?
1, 2,
Okay,
3.
just a little
Yeah,
bit.
just counting. Yep. All right. So again, the first bit will be a 0 since the number is positive. Haven't done the exponent yet, so leave a gap. What's going to go on the end?
Everything after.
Yeah, everything after the decimal point, right? This part goes on the end. 1, 1, 1, 0, 1, 1, 0. Oh, for heaven's sake, why does it keep jumping on me? 1, 0, 0, 1, 1, 0, 0, 1. We've typed in 1, or we've written 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many zeros do we need to fill on the end? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that part okay? Literally just taking the decimal, writing it in there, filling zeros until we hit 23 spots. Okay? Last thing we need to do is convert the 8 to an exponent, right? Now, again, we add 127 and convert it, right? So Austin already mentioned this a minute ago. When you add the 127, you get 135, because that's that shift that we have to do. Make sure that we allow for negatives. We need to convert your 135 to binary. So let me scroll up here real quick. I know I'm out of time. In binary, 135 is 1, 0, 0, 0, 0, 1, 1, 1. That's 1, 2, 3, 4, 5, 6, 7, 8 places already. Right? So there will be, what did I say, 1, 0, 0, 0, 1, 1, 1, 1. I missed a 0. Of course I did. There's our representation. So again, this part is your sign. This is your exponent. This is the mantissa part. Okay? All right. We'll talk just a little bit more about that on Tuesday, mainly so we can talk about hexadecimal representation. And then we'll jump into chapter 4, where we're going to start doing some derivative approximations. So have a good weekend, everybody.